All right, welcome to our 6th unit of AP Chems. This unit's on electrochemistry. Our first section's on oxidation numbers. So electrochemistry is the branch of chemistry that investigates basically the transfer of electrons amongst reactants. As in, they're not transferred to, we don't think of them more as going from reactants to products. We're more looking at them going from reactants to reactants. Now, it doesn't really change a whole lot of what we're looking at, but typically this ends up investigating electricity, hence electrochem. So a reaction in which a substance gains electrons is called reduction, and one in which a substance loses electrons is called oxidation. Those are the two biggest terms for the entire unit, reduction and oxidation. Again, reduction is when you gain electrons. It's called reduction because think of electrons having a negative charge, and as you gain more electrons, your charge is lowered or reduced. It also stems from the fact that when people really started looking at these, they mainly thought that oxidation, what we know today as oxidation, only occurred when it gained oxygen. So they took oxidation to think when you gain oxygen, and thus typically, for what we know now, you're losing electrons, and reduction is when you lost an amount of oxygen, which today is actually when you gained electrons. So the term comes from oxygen, but now we know of it more as gaining electrons is reduction, losing electrons is oxidation. These will always happen together, and so typically a reaction in which electrons are transferred, meaning one reduces and the other, or one gains, the other loses, is called an oxidation reduction reaction because we have both oxidation and reduction. Commonly, though, we just call that a redox reaction, with the red coming from reduction and the ox coming from oxidation. I'm not sure why it's not called ox-red, besides the fact that it's really hard to say ox-red, especially when compared to redox. But there you go, reduction and oxidation. To help you remember the difference, think of an oil rig. So oil rigs, by the way, are those things that are tall and got a platform. There's like a drill going into the earth, and there's a bunch of oil and stuff. I'm pretty sure that's what an oil rig is. But oil rig stands for, at least the O stands for oxidation, is losing. There you got oil, electrons. And reduction is gaining electrons, rig. So oil rig helps you remember what oxidation is and what reduction is. So in order to determine which species in a reaction loses or gains electrons, we use oxidation numbers. Now, these are semi-arbitrary numbers designed to help scientists keep track of the transfer. I say semi-arbitrary because they kind of relate to charges, but not always, and scientists kind of just started placing numbers and made their own pattern. So they're not always related to its electron config state, but sometimes it is, sometimes it's not. You don't really need to know that. I'm just letting you know why some numbers, you're going to find that they normally have a charge of like 2, and the oxidation number is like 8. You're like, wait, what? That is just weird. So, okay. This is our procedure to determine the numbers, our oxidation numbers. However, you always have to follow it in order. That means that number 1 is always the ones that are assigned first. Number 2s then get assigned next. Then number 3s, then 4, and finally 5. Now, they're not that hard if you go in order. So the first, that all free elements are 0. So if you've got, a free element, then its oxidation number is going to be 0. For ions, it is their charge. Okay, that means, for example, sodium plus will have an oxidation number of positive 1. Now, charges technically are written with the number first. We're telling you the overall net difference between electrons and protons. Oxidation numbers are all actual normal numbers. So an oxidation number of 1 is positive 1, not 1 plus. Or vice versa for sulfur. If it's just sulfur by its, S2 minus, sulfide, be negative 2. Oxygen is always a negative 2, and peroxides are negative 1. Peroxides are where you've got O2, but it overall has a charge of 2 minus. In this case, the charge can be -1. So normally oxygen's a -2. Sometimes, though, you'll see -1. All right, hydrogen is +1 with nonmetals and -1 with metals. These are the only two rules that can be kind of swapped. Some people put hydrogen first, some people put oxygen first. Just follow these rules. But like if you're ever stuck and you're looking online, you find someone else and they flip it, it's not that big a deal, as long as only these two are flipped. All right, lastly though, the sum is 0 in neutral compounds and the charge in ions. Meaning that if we have a compound called, let's say H2O, that the oxidation numbers of hydrogen and oxygen overall have to add to 0. Now, let me actually say that again. All the oxidation numbers, let me add, of each atom in the molecule have to add up to 0. That means that the oxidation number of one hydrogen plus the oxidation number of another hydrogen plus the oxidation number of an oxygen have to equal 0. Not necessarily them together. You'll actually find in this case that hydrogen will be +1 and oxygen will be -2. And 1 minus 2 is not 0. That's fine. That's not our issue. What we're looking for is that +1 times 2 plus a -2 times 1 with that 2 and 1, coming from our subscripts. This equals 2, or 0, sorry. Not these. These. Hopefully it makes sense. Let's get some practice though. Okay, so now that we're actually done, gotta actually change a few things. So, as you can tell, my eraser didn't really work, so I just kind of put a white square. There's actually one rule missing here. I'm sorry. It's basically going to be rule 4.5, if you will. And what that is that halogens, so I'm going to start writing in black. Halogens are typically -1. Okay? And these are going to be column 17. Might as well write that. They typically are 17. In addition, I want you to look up here. We're going to have 1A is +1, 2A is +2, and 3A is +3. Okay, so let me explain why I had to add these in. Long story short, I forgot to. But for ions being their charge, this mainly refers to monatomic ions, and most ions, when they're in ionic compounds, are going to act normal. They're going to be their own normal charge. However, that doesn't always happen. Especially with nonmetals, they tend to share a little bit more electrons than I guess we were thinking of. So our priority are these groups. They will not change. Okay, so 1A metals will be +1, 2A +2, and 3A +3. If you get to the point where your compounds don't quite add to 0, make sure these are staying their charge, and then basically you're going to start changing other things. So halogens typically are going to be -1, but these, if this being -1 does not work with one of these being +1, 2, or 3, then you change the halogens, because these will stay. So you'll see in a bit kind of what I'm talking about. Just try to remember those. All right, go ahead and pause the video, try these as best you can, and then come back in just a little bit and I'll help you with them. Okay, welcome back. Let's work on a couple of these. Let's just work. So H2S, it's not a free element. There's no ion. There's actually no oxygen. It means our first one's going to be hydrogen. Now I typically write my oxidation numbers up top. I think I may start circling them, because then what I use is down here is kind of like my scratch paper, and up here is my final answer. Scratch paper wise would then tell me that total I've got 2 positives coming from hydrogen. Now this whole thing doesn't have a charge. That means it's neutral. That means that my total sum of oxidation numbers have to add up to 0. Well, I've got 2 positives. That means sulfur is going to ultimately have to bring 2 negatives. Okay, these will add to 0. And now I realize that, hey, I've only got one sulfur. That says that ultimately my sulfur is going to bring all those two negatives. So my oxidation number for sulfur in that one is -2. All right, so let's do the next ones. Next one's S8. Kind of weird, but that's actually how sulfur comes in its normal state. Thing you got to realize, though, is that's the only element in this compound, which means that A, the overall compound has a neutral charge, or B, we can just go off our first rule, which says free elements are 0, and there you go, your answer is 0. That was really hard. All right, let's go to the next one. SCl2. Okay, so we've got that free elements are 0, ions are their charge. So let's look into this. Typically, chlorine has a 1- charge, and sulfur typically will have a 2- charge. Well, 2- charge, which means -2. However, if I multiply those out, I get a -2 and a -2. Yeah, that's not fun. So we got to go back to those rules that I had you in. One of those rules said that halogens stays at a -1. Well, chlorine happens to be a halogen, and sulfur is not. That means in this case, since chlorine actually was factored in by our rules, we're going to be changing sulfur to get this to work. So though sulfur normally is -2, in this case, chlorine has to be -1, which means for a total of -2, we need a +2. That means in this case, sulfur is going to be a +2. Now, again, we're going back to those rules that, yes, I did have to add in. Sorry about that. But that's basically how you do this. You just simply get things to work. All right, let me show you the next one. All right, Na2, SO3. Okay, we don't have a free element. We do have ions that are typically their charge. Oxygen typically is -2. Sulfur is a group 1A metal, so even more so that's going to be a +1. And I'm going to hold off on sulfur because I know these two are factored in by rules, but I want to make sure that sulfur can actually stay its normal charge. Okay, so sodium's going to have a total of +2, oxygen -6. That gets us a total of like -4. That means that in this case, -4. To get all this to 0, sulfur is going to have to be a +4 as well, which, as I kind of figured, it's not actually its normal charge. I'll also circle all these. So again, go off the rules. That doesn't make sense. Go off the rules unless some elements, they can't get to 0, then you change whichever one isn't applied to the rules, or at least is applied lowest on the rules. All right, and then our last example, SO4, 2-. Now, same as what we've been doing, the only difference is that we have to add to -2, not 0. But oxygen is going to be -2. That gets a total of -8. Sulfur is our last one to add. It is typically -2, but I should probably guess it. It's probably not in this case. If we need to get to -2, sulfur needs to be +6. That means +6. There you go. So again, free elements, and then most things are their charge. However, it may actually just benefit you more to just assign group 1A, 2A, and 3A. I will probably change that for next year, so yeah, for now, let's just go with that. Unless they're by themselves, mainly assign group 1A, 2A, and 3A for now, and then come back and fix everything else as it needs. That's oxidation numbers. All right, now we're going to figure out what species oxidizes and what species reduced. This is typically what you do in problems. You actually assign all the oxidation numbers and basically figure out what happened. All right, so free elements are 0. We don't have any. And actually, before that, go and try this. Spend a few minutes, try and assign all them, figure out what oxidizes, what reduces, and yeah, come back. All right, let's start assigning these. So we don't have free elements. We do have a monatomic ion, though. That's going to be +2. I'm writing it down here just because I don't actually have room. Normally, though, I write it on top. All right, so now we got group 1A, 2A, and 3A metals. We don't have any of those. So we move on to oxygen being -2. I guess I have space up there for that one. You know what? Hang on. All right, so I basically just rewrote the equation. Alright, so we got oxygen done. Now, we don't really have any rules that deal with copper, carbon, or manganese, so we kind of just get things to be what they need to be. So, on the far left, this needs to add up to a -1. We already have a -8. That means manganese is going to have to be a +7. On our next one, we have to add up to a -2. That means carbon has to be a +2. Thus, we get a +1. And the last one has to add up to 0. That means carbon has to be +4. That means +4. Alright, so here's where we got reduction and oxidation. For reduction, you figure out which one reduced. Manganese went from +7 to +2. That is what we call reducing. Or we call it reduction too. Okay. Then let's look at oxygen, -2, went to -2, didn't apply. Carbon, went from +1 to +4. There we go, that's increasing. Thus, oxidation. Sign the numbers, figure out what went up and what went down. So that means that our reduction reaction, as we're going to show in a bit, is MnO4 minus to Mn2 plus, and our oxidation reaction is C2O2 to CO2, meaning you don't just take the carbon out, you do the actual whole molecule. There you go, that's oxidation numbers.